Imagine a powerful force that can shape entire galaxies but is hidden from view. A vision of light and a warping of time that try to escape us. It is a reality of a supermassive black hole lurking at the center of countless galaxies, including our own. But the story does not end there. Recent discoveries have proven that these space giants are not just passive consumers of matter. They influence the structure of the universe, play an important role in the formation of stars, shaping the evolution of galaxies, and even the creation of planets like Earth. Today, we delve into the hidden mechanisms behind these forces and explore the revolutionary changes that ultimately reveal these mysteries. What we discover could change our view of the universe forever. First, let's talk a little theory, making sure we're on the same page. Let's start with quasars, which serve as the energetic hearts of active galaxies in the universe. Powered by supermassive black holes, these bright beacons radiate the collective light of all the stars in the galaxies. In our case, a subset of quasars called red quasars has attracted the attention of astronomers. Unlike their blue counterparts, red quasars are covered in cosmic dust, which plays a key role in their unique properties. The observed reddening of quasars is a direct effect of the dust surrounding them. Dust absorbs short, blue wavelengths and lets in longer, red wavelengths. This phenomenon not only changes their appearance, but also enhances their radio emission, as recent studies using data from the Dark Energy Spectroscopic Instrument, or DESI, and the Low-Frequency Array LOFAR have shown. Victoria Fackett and her team at the University of Newcastle found that red quasars emit stronger radio signals than their dust-free blue counterparts. Powerful radiation streams from the quasar collide with the dust, exciting the molecules inside and causing them to emit radio waves. This interaction is key to understanding why red quasars are stronger in radio air. But why are these red quasars so important? The answer lies in their age and stage of evolution. Red quasars are thought to represent the young stage of the life cycle of active galaxies. The dust covering them is not just an obstruction, but a remnant of the galaxy's past, likely formed during star formation, the period of violent stars formed by galactic mergers or other dramatic interactions. As the supermassive black hole continues to feed, its currents slowly shake off this veil of dust, revealing a blue quasar with radio emission in its place. This explosion phase refers to the evolution of a quasar from a dusty, radio-intense form into a blue quasar with purged, quenched radioactivity. Observing red quasars gives astronomers insight into the early stages of this transformation and provides valuable information about the mechanisms that govern the evolution of galaxies. The discovery of thousands of red quasars by Fawcett's team underscores their importance in the cosmic landscape. These objects are not just rare anomalies, but important pieces of the puzzle for understanding the evolution of galaxies. As supermassive black holes grow and expand, so do their galaxies, and the activity of quasars plays a key role in this dynamic process. Now that we understand the basics, we can continue our journey and delve deeper into the explosion phase and its impact on the evolution of galaxies. The explosion phase theory provides a deeper understanding of the life cycle of red quasars in the centers of young active galaxies. This stage represents a critical period of evolution, when the supermassive black hole at the center begins to purge itself of dense clouds of gas and dust. And this turns the galaxy from a red quasar to a blue one. At the heart of this theory is the enormous force created by the supermassive black hole, which is powered by the material of the accretion disk. The intense gravity within the disk creates friction, heating the gas and dust to millions of degrees. This advance not only illuminates the quasar, but also releases energy that leads to the explosion phase. Consisting of high-speed winds and magnetized jets, These jets act like cosmic brooms, sweeping away dust and gas. As these jets collide with the material, they create shock waves that further accelerate the cleaning process. Over time, this cleaning opens up the interior of the quasar, reducing the amount of dust and allowing the quasar to shine brighter in optical and ultraviolet wavelengths, a phase we now call a blue quasar. This theory is supported by observations made by space telescopes. JWST's infrared capabilities allow astronomers to penetrate the dust and obtain detailed images and data that reveal the dynamics of this explosive phase. In particular, these observations reveal interactions between quasar jets and surrounding matter, consistent with the process of ejecting dust and gas from the galactic center. These results are in good agreement with the predictions of the burst phase theory and indicate that red quasars are indeed in a transition state. Now, as an example, let's turn to the news itself. Several times, and we go again, the James Webb Telescope has opened a new chapter in our understanding of space. Among the many discoveries, the case of the galaxy ESO428G14 stands out. Located about 70 million light-years away, an active galactic nucleus, or AGN, is a region centered on a supermassive black hole that exerts a powerful influence on its surroundings. ESO428G14 is not just any galaxy. An AGN is a powerful radiation source covering the entire electromagnetic spectrum, caused by a supermassive black hole absorbing matter at extraordinary speeds. This phenomenon creates a large amount of energy, making active galactic nuclei one of the most luminous objects in the universe. But what has attracted astronomers' attention is the recent discovery of shock elements in the clouds of dust and gas surrounding the black hole, which have complicated our understanding of how these cosmic giants interact with their surroundings. Most theories assumed that the energy heating the surrounding dust in the AGN came directly from the supermassive black hole. However, the JWST observations revealed something even more interesting. The energy heating the dust comes not only from the intense radiation of the black hole, as well as from strong interactions with jets of gas ejected from the black hole's columns at the speed of light. These jets collide with the surrounding matter in what astronomers now call shock waves. These influencers were a revelation. Previously, scientists debated how active galactic nuclei transfer energy to their surroundings. It was surprising that radio jets could cause so much damage to nearby dust and gas. The discovery challenges long-standing assumptions and opens new questions about the dynamics of supermassive black holes. The implications of these findings are profound. By detecting the interaction between radio jets and surrounding matter, JWST is revealing how supermassive black holes affect not only their surroundings, but the entire galaxy. Once thought to be a simple byproduct of black hole activity, these jets now appear to play an important role in shaping the environment, influencing the rate of star formation and the overall structure of the galaxy. This phase is an important element in the complex interactions between supermassive black holes and their galaxies. To better understand the effect of active galactic nuclei on the surrounding space, let us study the feedback mechanisms that regulate the interaction between supermassive black holes and their cosmic neighbors. It has long been known that at the center of many galaxies, there is a supermassive black hole, also known as an AGN, surrounded by a dynamic and turbulent environment. An AGN is a region of strong energy fluxes driven by strong radiation and an accretion disk, the giant structure of gas and dust that feeds a black hole. This disk, heated to millions of degrees by its immense gravity, emits radiation across the entire electromagnetic spectrum, from X-rays to radio waves. The accretion drive is not a uniform structure. It has distinct regions that behave differently depending on its proximity to the black hole. In the inner regions, matter rotates at incredible speeds, generating enormous amounts of heat and emitting high-energy radiation. But recent observations have provided new insights into the outer edges of these disks. For the first time, astronomers have observed the outer edge of the accretion disk, providing a more accurate picture of its size and structure. Using the James Webb Space Telescope and infrared spectrograph by Young, the researchers detected emission lines in the infrared spectrum from the distant quasar 3Z002. These lines, broadened by the Doppler effect, show the size of the accretion disk, confirming its width and the turbulent conditions within it. The authors of the study hypothesize that these emission lines occur when atoms in the disk absorb energy, enter an excited state, and eventually return to a lower energy state, emitting light. The unique double profile of these lines, due to the rotation of the disk, allowed astronomers to measure the size of the disk and helped to understand the behavior of matter in the influence of the supermassive black hole. The accreditation drive is not the only actor. At the AGN Theater, radio jets shoot out from the accretion disk's poles, streams of charged particles accelerated to the speed of light by the black hole's magnetic fields. These jets are not just products, but powerful forces that shape the environment around the active galactic nucleus. Colliding with the surrounding dust and gas, they generate massive shock waves that affect the evolution of the entire galaxy. The interaction of these jets with the interstellar medium can cause star formation in some regions and collapse in others. This feedback mechanism, known as AGN feedback, plays an important role in regulating galaxy growth. By enriching or stripping the surrounding gas of heavy elements, these jets can dictate the rate of galaxy growth, effectively controlling the balance between star birth and death. In addition to jets, black holes exert their effects through tidal disruption events, or TDEs, when a star comes too close to a black hole and is pulled apart by gravity. This process, called spaghettification, causes the star to stretch and collapse, with some material falling into the black hole and the rest being ejected into space. Recent studies have confirmed that not all of the star's material is absorbed by the black hole. Instead, most of the gas escapes, forming a large spherical cloud that can mask high-energy radiation such as X-rays. Detected using polarized light, this cloud provides insight into the effects of TDE when the black hole's appetite leaves a visible trail around it. But this dust is not just tiny particles floating in a vacuum. It plays an important role in shaping our understanding of the universe and contains fundamental information about the processes that govern the cosmos. Cosmic dust, often thought of as simple space debris, plays an important role in complex processes in the universe. Cosmic dust is formed mainly from stellar debris and consists of micron-sized particles, the size of a human hair, and elements such as carbon, silicon, and metals. These particles are killed not only by the phenomena discussed above, but also by various interstellar events such as supernova explosions, when stars eject their outer layers into space, or by the gentle pulverization of matter by red giants. The formation of cosmic dust is evidence of the life cycle of stars. In the case of a supernova, a powerful explosion scatters heavy elements into space, which eventually cool into dust grains. Thus, as red giants expand and lose their outer layers, they slowly expel material between stars, contributing to the formation of cosmic dust. This dust can later be incorporated into new stars, planets, and even life, making it an essential component of space processing. But cosmic dust is not only a product of stellar evolution. This has profound implications for how we observe the universe. One of the most serious problems caused by dust is its ability to obscure our view of celestial objects. Dust particles can scatter and absorb light, especially in the visible spectrum, making it difficult to see through dense clouds around galactic centers, or active galactic nuclei. This obscurity is especially problematic when studying black holes and quasars, where the presence of dust can obscure the most interesting features. However, as we mentioned above, JWST's advanced infrared capabilities allow it to penetrate the visible range of the spectrum. Through infrared observations, JWST will be able to detect heat emitted by dust particles, as well as light from objects hidden behind or within clouds. As we continue to unravel the mysteries of space, the future looks even more promising with the Nancy Grace Roman Space Telescope. It will be launched in 2027 and will complement JWST by taking infrared images that are 200 times larger than Hubble, but with the same level of detail, offering a wide panoramic view of the universe. The novel's extensive field of vision will allow him to collect an unprecedented amount of data, providing information on billions of galaxies and helping to create a three-dimensional model of the universe. This telescope will not only expand our understanding of cosmic dust and its role in galaxy formation, but may also answer some of the big questions in astrophysics, such as the nature of dark energy and the structure of the universe on the largest scale. Whether it's mapping the expansion of the universe or discovering a new exoplanet, the future of space exploration holds endless possibilities. Thanks to revolutionary technologies, we are on the verge of unlocking secrets that will change the way we think about space. Be curious, because the universe is full of mysteries waiting to be discovered. At one point in our lives, we wondered if we were alone in the universe. With so many planets orbiting multiple stars in our own or other distant galaxies, why haven't we encountered signs of extraterrestrial life yet? But what if evolved alien life forms survive and hide? A dark front, SATI hypothesis, that technologically advanced civilizations may have developed outside the solar system. But they are not going to make contact because they fear attacks from other civilizations, or they are preparing for an attack. Today, you will learn about the dark forest theory and why you should avoid anyone who can hear you in the vast space. 1. The dark forest hypothesis. Author and primary source. The author of the dark forest hypothesis, DFH, is science fiction writer Liu Cixin. It should be noted that this is not a scientific theory, and it is not based on any concrete evidence. In 2008, Liu Cixin published his best-selling science fiction novel. The dark forest theory is presented for the first time in this book. The essence of the theory is that each spatial civilization seeks to obtain the resources necessary for its continuation. Thus, life on Earth is hidden to prevent another civilization from being destroyed, to attack and ensure its survival. So why is this theory called the dark forest hypothesis? In his novel, Liu Cixin compares a dangerous existence to a forest inhabited only by hunters. The author describes the civilizations as metaphorical armed men in the dark forest, who advance silently for fear of being discovered by hunters. If one hunter can detect the other, he attacks first before his opponent does the same. With this in mind, there are several ideas that promote DFH. The first is that there are hypothetical alien civilizations. They hide because of the threat of attacking others and losing resources such as living planets. Within the black forest hypothesis, the foundation of every civilization is known as the chain of suspicion. This phenomenon is caused by a lack of communication, which directly leads to mistrust. A second idea is that a civilization that actively transmits radio signals and gives away its space can be invaded or destroyed by others for resources. A third concept is that communication is rare in this type of system because each civilization seeks to survive, primarily through expansion. However, an agreement is possible if its terms are beneficial to both civilizations. Liu Cixing portrays the universe as a battleground for limited resources, where alliances are almost impossible. Finally, in Liu Cixing's hypothesis, hunter-gatherers are similar to high-tech civilizations. Therefore, if a civilization is not advanced enough to show itself in space, it will be ignored or become an easy victim. 2DFH is the answer to Fermi's paradox. As you know, in 1950, the famous physicist Enrico Fermi, while discussing the flying saucer with his colleagues, suddenly asked, "Where is everyone?" referring to extraterrestrial life examples that illustrate the origin of the famous Fermi paradox. We talked about it at length in this video on our channel. Fermi, if our galaxy was formed several million years before the birth of humanity, other civilizations much older than Earthlings may have arisen during this period. This means that the Milky Way galaxy should be full of civilizations that can receive our signals due to our technological advancements, as well as travel across the galaxy. However, so far, we have seen no sign of alien activity. Why are they on Earth and not approaching our planet? Determine the number of extraterrestrial civilizations within our galaxy. The famous Drake equation was derived in 1961, but we cannot use it to explain why aliens leave no signs of life. Therefore, at this point, there is only a theoretical explanation for the Fermi paradox. Furthermore, according to physics professor Adam Frank, the probability that Earthlings are the only civilization in the universe is very low. 1 in 10 billion trillion, or 10 to 22 powers. The professor suggests that our evolution is not unique, and that other civilizations may have preceded us or been much longer than us. There are more than 70 hypothetical solutions to this question, one of which is the Black Forest hypothesis. Of course, we cannot test the validity of DFH due to current technological limitations, but Liu Cixing's theory provides a logical explanation for why we have yet to receive any alien signals or find signs of life on other planets. It is dangerous for other civilizations to give up their land for fear of invasion. Although this hypothesis presents very clearly defined ideas, there are some inaccuracies in DTH. For example, if there are other civilizations, they must differ from ours because of different degrees of gestation, Fermi noted. This means that there may be civilizations at or above our technological level that actively seek out alien life or explore their own systems like we do because they don't see it as a threat. So we are not just signalers, because civilizations don't grow out of fear of discovery if they don't face opposition. Third, more about the assumptions of the Dark Forest hypothesis. The idea of conquering other territories and destroying the first civilization on a cosmic scale is reminiscent of our historical experience on Earth, namely colonization and war. There are many reasons why people conquer other nations. However, in most cases, such as during the European colonization of Africa in the 19th century, the main motive was land and natural resources. The rapid growth of industry in Europe required resources available elsewhere on the continent. Thus, the colonization of Africa helped the development of European countries, but the African land and its people suffered from this expansion. DFH presents the same colonial model as the reason for one civilization attacking another. We are still looking to expand for the continued existence of humanity, explore exoplanets and other star systems, and plan to colonize Mars. The red planet is also rich in natural resources for technological development. So, assuming that other civilizations have similar goals, we may have to fight for lands that can serve humanity. Otherwise, our survival would be in danger because, according to this hypothesis, survival and the necessary resources are essential to the preservation of the species. Besides the need to replenish a limited resource, there are other reasons for the aggressive behavior of civilizations. For example, as we discussed earlier, DFH introduces a concept called chain of doubt. This concept is closely related to another aspect of this hypothesis called technological explosion. The essence of the chain of suspicion is that civilizations cannot know whether others are benevolent or hostile. These doubts can lead to preemptive attacks and self-defense. According to researcher Chao Yu, this chain can only exist among civilizations with a high level of technological development, because they can objectively assess their own and others' capabilities. Thus, if there is a large difference in their development levels, a chain does not form. Technological explosion describes the ability of space civilizations to make rapid scientific and technological leaps. Powerful new hunter may pose a threat to others because advanced civilizations may fear it or seek to destroy it. However, Chao Yu notes that any attack can also infect the attacker, as other civilizations with similar or higher levels of development can detect it, thus creating a chain of suspicion. However, despite the obvious advantage in attacking other civilizations and hideouts, the DFH is considering another scenario: kindness. The purpose of the bounty is to refrain from attacking other civilizations that, even if detected, are unlikely to be able to respond to the signal. In the dark forest, this tactic is dangerous because it reinforces the chain of suspicion. Another civilization identified with a benevolent civilization is aggressive or rapidly growing, so he can destroy others in the future and live by collecting enough resources, while the benevolent civilization will be destroyed. If we think that extraterrestrial life exists and it's far ahead of us, it might attack us because it's a survival tactic with the highest chance of success. This is not good news. So, other than an invasion of our planet, are there any viable options for Earth based on the dark forest hypothesis? Let's look at this from a game theory perspective. Number 4. Game theory and DFH. The main goal of game theory is to study how people make decisions based on certain circumstances in order to achieve the best possible outcome. Imagine that Earth is a civilization and advanced alien life is a civilization. B received the radio signal. Now B has 3 strategies: attack, don't be obvious, but be suspicious, or respond in the hope of friendship. Even if A fights back, attacking will be considered the most favorable strategy. On the other hand, according to researcher Alina Su, this scenario could be a loss for B if Planet B could send a signal to transfer its coordinates to other civilizations. Perhaps the best option in this case would have been to remain unclear. If both civilizations do nothing, good will not work either. On the one hand, it will put A and B out of danger, and on the other hand, they will not be able to get the resources they need. There is also an opportunity to become friends. If 2 civilizations agree to an alliance, one of them will gain advantages such as the ability to use foreign technology. Other civilizations that offer friendship will also benefit, albeit to a lesser extent. Does this alliance mean the best-case scenario for both civilizations? Maybe, but it comes with some pitfalls. First, kindness, as you know, is very dangerous because hypothetically extraterrestrial civilizations are not likely to be friendly very often. Second, the amount of available resources, even in the case of a trade agreement, is less than that obtained by force. Thus, the probability of a theoretical attack on Earth is the highest, but this course of events could seriously damage the attacker. However, other civilizations may fear Earth's unknown military potential. So, choose stealth or friendly tactics. 5. Does the risk of sending a signal into space mean that we should avoid sending a signal into space if the probability of a ground attack is higher than the other options? According to the DFH, messages to other civilizations could threaten our security. This is the same idea as PYY many astrophysicists, including Stephen Hawking. Since the breakthrough in space exploration in the middle of the last century, Scientists have shown great interest in the search for alien civilizations. In 1974, the famous Arecibo message was sent to a star cluster 21,000 light-years away. Since then, several radio messages have been sent into space, the most recent of which dates back to 2017. Physicist Stephen Hawking believes these messages could lead to the scenario described in the dark forest. According to him, the arrival of an alien civilization on Earth could have the same consequences for us as the colonization of America in the 15th century. Therefore, he believes that this type of communication should be stopped. However, other scientists, including SETI astrobiologist Douglas Vakoch, believe that fear of sending messages could lead to Earth's isolation. In addition, Vakoch noted that alien civilizations could invade our planet while it was still developing, so we should not be afraid to hear about extraterrestrial life. Finally, the dark forest hypothesis also promotes the idea of differences in hunter-gatherer behavior. That is, all civilizations will not attack us if they find our signal